Preparing for a data platform engineering at JPMorgan Chase interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a cloud data platform that supports both batch and real-time processing for financial transactions? I would separate ingestion, durable storage, processing, and serving layers. Kafka would capture transactions with replicated topics, while object storage would retain immutable history for replay and analytics. Spark structured streaming would handle near real-time enrichment, and scheduled Spark jobs would support backfills. I would add schema validation, encryption, access controls, lineage, monitoring, and reconciliation checks. For JPMorgan, multi-region recovery, auditability, idempotent processing, and strict data quality controls are essential because financial correctness matters more than raw throughput. While answering, cover ingestion, storage layers, Spark processing, Kafka streaming, schema management, orchestration, data quality, security, lineage, disaster recovery, and latency versus cost trade-offs. Question 2. Explain how Spark executes a job, and describe how you would diagnose a slow Spark pipeline. Spark builds a logical plan, optimizes it, creates a physical plan, and divides execution into stages separated by shuffle boundaries. The driver coordinates tasks, while executors process partitions. For a slow job, I inspect the Spark UI for long stages, skewed tasks, spills, excessive shuffles, and failed retries. Then I review partition counts, join strategies, file sizes, serialization, and caching decisions. I tune only after identifying the bottleneck, because unnecessary configuration changes can hide the real problem. Make sure to cover drivers, executors, DAGs, stages, tasks, shuffles, partitioning, Spark UI, skew, serialization, caching, spill, adaptive query execution, and measuring before tuning. Question 3. How would you choose Kafka partitioning for a high-volume transaction topic? I would choose a stable business key, such as account or transaction stream identifier, when per-key ordering is required. Hash partitioning distributes different keys while preserving order within each partition. I would estimate throughput and consumer parallelism, then select enough partitions for growth without creating operational overhead. Replication, acknowledgements, retention, and monitoring must match recovery requirements. I would avoid random keys when ordering matters and recognize that increasing partitions can change key placement and complicate downstream assumptions. In your answer, discuss ordering guarantees, partition keys, consumer parallelism, throughput, hot partitions, key evolution, replication factor, retention, and the consequences of changing partition counts. Question 4. How do you achieve exactly once or effectively once processing in a Kafka and Spark pipeline? Exactly once requires coordination across source offsets, processing state, and the destination. Spark structured streaming checkpoints offsets and state, while transactional or idempotent sinks prevent duplicate effects. I would carry a unique transaction identifier, enforce deduplication at the sink, and make retries safe. Kafka transactions can help within Kafka, but external databases still need transactional integration or idempotent writes. I would describe the guarantee precisely, because effectively once behavior is often more practical than claiming universal exactly once semantics. Be sure to mention delivery semantics, checkpoints, transactional writes, idempotency keys, offset coordination, deterministic transformations, retries, sync behavior, and why end-to-end exactly once is difficult. Question 5. What causes data skew in Spark, and how would you fix a skew join? Data skew occurs when a few keys own disproportionate data, causing certain tasks to run much longer than others. I would confirm it through Spark UI task metrics and key frequency analysis. If one side is small, I would broadcast it. For hot keys, I could salt keys on the large side and replicate matching rows on the other side, then remove the salt afterward. Adaptive query execution may split skewed partitions automatically. The right fix depends on data shape and join semantics. Focus on identifying uneven key distributions, interpreting task duration metrics, salting hotkeys, broadcasting small tables, adaptive skew handling, repartitioning, and preserving correctness during mitigation. Question 6. How would you design a reliable Kafka-to-Spark structured streaming pipeline? I would read Kafka with a durable checkpoint location, validate records against a versioned schema, and route invalid events to a dead letter topic. Structured streaming would use event time, watermarks, and bounded state for aggregations. I would select a trigger based on latency targets, monitor input rate, processing rate, lag, and checkpoint health, and configure restart policies. The sync would be idempotent. I would also test late events, duplicate delivery, broker outages, and checkpoint recovery before production. Cover consumer offsets, checkpoints, watermarking, windowing, late data, state growth, trigger intervals, output modes, back pressure, dead letter handling, schema validation, and operational alerting. Question 7. How would you implement data quality checks for a regulated financial data pipeline? I would define checks with data owners, required fields, valid ranges, referential integrity, uniqueness, freshness, and record count reconciliation against source systems. Failed records would be quarantined with reason codes, while critical dataset failures would stop publication rather than silently propagate corruption. Metrics and rule versions would be stored for auditability, with alerts routed to accountable teams. I would distinguish hard failures from tolerated anomalies and regularly review thresholds, because overly strict rules can block legitimate financial activity. In your answer, include completeness, validity, uniqueness, accuracy, reconciliation, thresholds, quarantine paths, lineage, audit evidence, alerting, ownership, and handling failures without silently publishing bad data. Question 8. Compare Parquet, Avro, and JSON for a cloud data platform. JSON is flexible and readable, but verbose and expensive for analytics. Avro is compact, row-oriented, and well-suited to Kafka because it carries or references an evolving schema. Parquet is columnar, compressed, and ideal for analytical queries in cloud object storage because engines can read only required columns. I would typically use Avro or another schema-aware format at ingestion, then convert to Parquet in curated lake layers. Compatibility rules must be enforced so producers do not break consumers. Discuss row versus column orientation, schema enforcement, evolution, compression, query performance, interoperability, human readability, streaming suitability, and appropriate choices for Kafka, lake storage, and APIs. Question 9. What is a medallion architecture, and how would you apply it to a financial data lake? A medallion design separates raw ingestion from progressively trusted data. Bronze stores immutable source events with ingestion metadata. Silver applies validation, deduplication, standardization, and conformed keys. And gold exposes business-ready aggregates or serving tables. For financial data, I would preserve raw records for replay and audit while restricting sensitive access at every layer. Transformations should be versioned and reusable, not copied into dashboards. The architecture improves recoverability and governance, but it still requires clear ownership and retention policies. Make sure to explain bronze, silver, and gold layers, immutability, cleansing, conformance, business aggregates, replayability, access controls, retention, and preventing duplicated logic across layers. Question 10. How would you handle schema evolution for Kafka events consumed by multiple teams? I would use a schema registry with compatibility checks enforced in C and at deployment. Additive changes should generally introduce optional fields with safe defaults, while removals require consumer migration and a deprecation period. Producers and consumers need contract tests against representative versions. I would roll out consumers before producers when necessary, monitor deserialization failures, and document ownership. For critical financial topics, I would avoid silent coercion and maintain an explicit migration plan rather than relying on informal coordination. Cover schema registry, backward and forward compatibility, optional fields, defaults, versioning, consumer contracts, rollout sequencing, testing, deprecation, and avoiding incompatible changes in shared topics. Question 11. How would you secure a cloud data pipeline handling personally identifiable and financial information? I would classify data first, then apply least privilege IAM, private networking, encryption in transit and at rest, and centrally managed key rotation. Sensitive fields should be tokenized or masked before broad analytical access, with row or column level policies where supported. Secrets belong in a managed vault, never in code or notebooks. I would log access and administrative actions, enforce retention and deletion policies, and regularly review permissions. Security controls must be automated through infrastructure and deployment pipelines. Discuss encryption in transit and at rest, IAM least privilege, network isolation, secrets management, tokenization, masking, row-level controls, key rotation, audit logs, and compliance-driven retention. Question 12. How would you make a Spark pipeline cost-efficient in the cloud without sacrificing reliability? I would first reduce data scanned through partition pruning, column projection, incremental processing, and compact columnar files. Then I would tune executor sizing, auto-scaling boundaries, shuffle partitions, and workload scheduling. Caching is useful only when reused enough to justify its memory cost. Spot capacity can lower expenses for retrievable jobs, but critical workloads need resilient fallback capacity. I would tag resources, monitor cost per dataset or pipeline, and balance savings against latency, recovery time, and operational risk. Focus on partition pruning, column projection, file compaction, appropriate formats, auto-scaling, workload isolation, spot capacity trade-offs, caching, incremental processing, and cost observability. Question 13. Design a disaster recovery strategy for a Kafka and cloud data platform. I would define recovery point and recovery time objectives with business stakeholders before selecting technology. Kafka data could replicate across zones or regions, while immutable cloud storage provides an authoritative replay source. I would back up schemas, checkpoints, orchestration metadata, and infrastructure definitions, not just data files. Failover procedures should address producers, consumers, credentials, DNS, and downstream services. Regular game days would validate recovery. The design must state whether failover is active-active or active-passive and how duplicates are reconciled. Be sure to cover RPO, RTO, replication, cross-region recovery, immutable storage, metadata and checkpoint backup, failover testing, replay, dependency mapping, and consistency during regional outages. Question 14. How would you process late arriving and out-of-order events in a streaming transaction pipeline? I would use event time because transaction occurrence matters more than arrival time. Watermarks bound state while allowing a defined lateness interval, and windowed results can be updated until that boundary. Events arriving later would go to a correction path or trigger targeted recomputation, depending on reporting requirements. I would preserve event identifiers for idempotency and monitor lateness distributions. The lateness policy should be agreed with consumers, since lower latency usually means accepting more corrections or incomplete results. Explain event time versus processing time, watermarks, allowed lateness, state retention, corrections, retractions, idempotency, business tolerances, and monitoring events arriving beyond the watermark. Question 15. What observability would you build for production data pipelines? I would monitor 4 dimensions: infrastructure health, application behavior, data quality, and business outcomes. Key signals include Kafka consumer lag, input and output rates, batch duration, failed tasks, checkpoint age, freshness, null rate changes, reconciliation counts, and unusual transaction volumes. Structured logs should include pipeline, dataset, run, and correlation identifiers. Dashboards need clear owners and severity-based alerts. I would connect lineage to incidents so engineers can quickly identify affected consumers and communicate impact accurately. Mention infrastructure, application, data, and business metrics. Kafka lag, freshness, throughput, failure rates, lineage, structured logs, traces, dashboards, alert thresholds, and actionable incident ownership. Question 16. How would you build an incremental pipeline that supports backfills and reprocessing safely? I would store immutable inputs and process by explicit event or business date partitions, recording each run's code version, input range, and output status. Writes would be idempotent through deterministic keys or partition replacement, never blind appends. A backfill would run in an isolated range, validate counts and aggregates, then publish atomically or merge carefully. Streaming checkpoints would remain separate from batch replay state. This makes recovery repeatable and prevents a historical correction from duplicating live records. Cover immutable inputs, partitioned processing, idempotent writes, run metadata, override scope, dependency ordering, late corrections, checkpoint handling, validation, and separating historical replay from live traffic. Question 17. When would you use a broadcast join, shuffle join, or sort merge join in Spark? A broadcast join is effective when one relation is small enough to fit safely in each executor, avoiding a large shuffle. A shuffle hash join can work when partitioned data and memory support hash tables, while sort merge join is dependable for large relations because it scales with distributed sorting. I would inspect statistics and the physical plan rather than force hints blindly. Skew, executor memory, and spill behavior matter. After choosing, I would validate runtime metrics and adjust based on evidence. Discuss table sizes, memory limits, network movement, join keys, skew, Spark statistics, adaptive execution, broadcast thresholds, and validating plans with explain and runtime metrics. Question 18. How would you design a multi-tenant data platform for different financial business units? I would standardize platform capabilities while isolating tenants through separate namespaces, access policies, encryption scopes, quotas, and workload queues. High-risk or high-volume domains may need dedicated clusters or accounts, while smaller teams can share governed infrastructure. Resource tagging enables chargeback and capacity planning, and limits prevent noisy neighbors. Each dataset needs an accountable owner, classification, SLA, and lineage. Central templates should enforce security and observability, but teams should retain enough autonomy to meet domain-specific processing needs. In your answer, address tenant isolation, shared versus dedicated resources, quotas, IAM boundaries, encryption, noisy neighbor control, chargeback, metadata ownership, service levels, and operational consistency. Question 19. Describe a time you would choose Kafka over a cloud queue or direct database extraction. I would choose Kafka when multiple independent consumers need a durable, replayable event stream with high throughput and partition-based ordering. A cloud queue is often simpler for work distribution where each message should be processed once by one worker. Direct database extraction may suit small, controlled workloads, but it can overload operational systems and couples consumers tightly to schemas. For financial systems, CDC into Kafka can preserve change history and support analytics without repeatedly querying the transaction database. Be sure to compare replayability, throughput, ordering, consumer independence, retention, operational complexity, transactional extraction, CDC, fan-out, and the business requirements driving the decision. Question 20. How would you investigate a pipeline that suddenly produces duplicate financial transactions? I would first define duplication using a business transaction identifier and quantify affected time ranges and consumers. Then I would trace producer retries, Kafka offsets, Spark checkpoints, batch reruns, join cardinality, and sync transaction logs. I would contain impact by pausing publication or deduplicating downstream views without destroying evidence. After identifying the boundary, I would make writes idempotent, correct checkpoint or retry configuration, and reconcile against the source of truth. Finally, I would add alerts, replay tests, and an incident record. Focus on defining duplicate identity, tracing offsets and retries, checking producer behavior, checkpoints, sync writes, reprocessing, joins, deployment changes, audit logs, containment, and permanent prevention. If you are still with us, congratulations! You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.